Hello, everybody. Today we'll be talking about model arithmetic and RSA. So till now, you would have probably gone about XOR and its functions. You would have gone through some basic encodings, ciphers, etc. Today we'll be jumping to the real deal. We'll be getting into the math behind cryptography, like the most basic math. Okay, and everything in cryptography relies on model arithmetic. So let's jump right in. So yeah, what is model arithmetic? So model arithmetic, you can think of it as wrapping numbers around a clock. So you know how clock has like only 12 possible digits, like 1 through 12. And if we reach, okay, if it's past 12 noon, okay, if it's 2, okay, we don't, some people call it 14 hours or 15 hours, okay, but most people refer it to as 2. Okay, that is essentially what this is. Okay, this is something we call congruence. Okay, in under mod 12, okay, mod is nothing but just taking the remainder. Okay, so you can just see if you just do 14 divided by 12, you end up with 2. Okay, so that is the remainder. So this is what we are trying to encapsulate as a mathematical operation called modular arithmetic, and all of it relies on just circling around numbers. So yeah. So yes, why modular arithmetic before that? So all of the crypto stuff, all of the advanced crypto stuff, even XOR can be expressed as a modular arithmetic. You can use a modular arithmetic notation for expressing that. So it would make sense for us to just dive right into the basic properties of what XOR can offer you. So yeah, so if we have like the basic addition property, so if you have a plus b, okay, you can take whole modern and that will be equal to a modern plus b modern whole raised to a whole modern. And subtraction, same holds with subtraction, a modern minus b modern whole modern will be subtraction. Same with multiplication. Okay, multiplication has a very interesting role in modular arithmetic, which we'll probably see sometime. And yes, this is very similar to day of the week arithmetic. So you can say Mondays, like we can denote it with 1, okay, plus 5 days, Saturday, okay, that will end up with Saturday, plus 5 will be 6. So Saturday will be the 6th day, and then we will cycle around again and again and again. So that is basic mode arithmetic. Now, I told you that modular, the multiplication part is a bit more, what to say, interesting in model arithmetic. So you saw multiplication having a certain property. So you would have been thinking, where is division? So inverse exists. Okay, inverse is the division for whatever this model arithmetic is. So what do you call an inverse element? In normal standard arithmetic, if we have, for example, 2, okay, the inverse of 2 will be just 1 by 2. Basically, a number 2 into some number, okay, should give you 1, or the identity element. Over here, 1 would be called as the identity element. And so if you multiply 2 into 1 by 2, you'll end up getting 1. And such is that we also have a modular, okay, identity element, 1 in this case for multiplication, okay, under mod n. So we can express model inverse as some number, okay, x, which when we multiply it with a, gives you 1 mod n. Okay, that is nothing but ax is congruent to 1 mod n. So in this example over here, you can see, okay, we are trying to find the modular inverse of 3 mod 7. All right. So we are trying out 3 into 1. It gives you 3 mod 7. So that is not the inverse. For inverse to exist, you need to get 1. Okay. For inverse to what inverse means is just getting 1 when you multiply some other number. So 3 into 2, okay, you are getting 6 mod 7. Still not 1. All right. 3 into 3 is 3 mod 7. Okay, not 1. 3 into 4 is 5 mod 7. And 3 into 5 finally ends you giving up 1 mod 7. And 1 is, again, your identity element, as I told you. So this is kind of interesting, right? So you have 3 multiplied by 5, okay, which gives you 1. Instead of normal arithmetic where you have 1 by 3, you have 5. So 5 and 1 by 3 perform the same kind of operation. You can say they are inverses okay, of 3. Only thing is 5 is the inverse under mod 7. It is not an inverse under anything else. Okay, it's an inverse under mod 7. So in mathematical notation, you can denote it as such. 5 is equal to 3 inverse mod 7. Note this minus 1 over here. Okay, it does not mean 1 by 3. 1 by 3, for your information, does not exist. Okay, it's only integers. When you're talking about modular arithmetic, only integers exist. So when we have 5, 3, 7, they're all integers, as you can see. You can all be obviously have negative numbers. Okay, but yes, raised to minus 1 does not indicate 1 by 3. It just simply indicates in this over here the congruent symbol that 5, when you multiply 3 with 5, you end up getting 1. That's it. So that is modular inverse. Okay, so we learned about a bit as like a start off with modular arithmetic. Let's just dive into crypto systems, okay, and let's see how modular arithmetic plays a role in them. So we have two types of crypto systems. We have symmetric crypto systems and asymmetric crypto systems. Symmetric crypto systems, okay, they use the same key. All right, they use the same key to both encrypt and decrypt the data. Okay, and asymmetric crypto systems, they have a public key and they have a private key, both one for encryption and one for decryption. And you can see symmetric crypto systems are like AES, DES, and asymmetric is RSA and ECC, such. RSA, again, this is the one we'll be studying, okay? And ECC is the current, what to say, if you go into your browser, you'll most likely see ECC implemented. ECC stands for elliptical cryptography. RSA we'll be looking at shortly, and this is where your modular arithmetic starts off. This is where you learn modular arithmetic and obviously then translate to ECC as well. And AES and DES, okay, these are other crypto systems that are very useful, AES especially, okay. But yes, the key difference is symmetric crypto systems use the same key to encrypt and decrypt, while asymmetric crypto systems have two separate keys called public and the private key for encryption and decryption, respectively. Now, okay, let's get past. Okay, now we are jumping back again into a modular arithmetic. This particular challenge, okay, we have something. This is exactly what is this? We are finding a number such that when you multiply it with 3, you should get 1. Mod 12. It's not mod 7 again, it's mod 12. So it can't be 5. Okay. So we are trying 1 mod 12. So you can ponder about this. Okay. If you want, you can probably pause the video if you're watching it after some time. But yes, we'll see why, okay, this particular case cannot be possible. Okay, that such that there is no x for which you can get a 1 over here. It's kind of interesting because when you think about it, 3 into 1 by 3 is such an easy thing. It's like every other number has an inverse. When you talk about this under under integers, like 5 has 1 by 5, 6 has 1 by 6, 7 has 1 by 7, so on, and 100 has 1 by 100, and you will get 1. But for modular arithmetic, you do not have inverses for every other number. So yes, why is that the case? So this is a very important property. For inverse to exist, the GCD of those numbers A and B should be 1. And what are A and B? Let's roll back. Over here, A and B would be 3 and 12. If you know GCD, you know the GCD is 3 over here. Okay, and from there, okay, we can go back. And we can see that GCD is not equal to 1. So the inverse does not exist. Okay. This is just a fancy way of just writing GCD. Okay. You call it Bezout's lemma. If you have the time, you can probably look it up. Okay. It's just A into X plus B into Y should give you 1. So, and where X and Y are some other numbers, which, okay, basically, and 1 is just a GCD. Okay. This should be equal to the GCD. X plus BY should be equal to GCD. This is what you call Bezout's lemma. So yes, in at the core, for inverse to exist, GCD of those two numbers should be 1. Otherwise, the inverse does not exist for that particular number. So yes, we learned about all this small arithmetic modular inverses, very specifically modular inverses. Now, again, we looked at the crypto systems part and we saw RSA and ECC, but RSA mostly. And I told you that we'll be learning about RSA shortly. RSA is such a system which uses modular arithmetic heavily, like extremely, like it's entirely based on modular arithmetic. So this will be like a nice practice, okay? And this is, as you'll see, is implemented and it's a very old, standard, okay, old crypto standard. So yes, a brief overview on RSA. So it's a widely used public key crypto system for secure data transmissions. I mean, really widely. It's been in use for decades now. Okay, a couple of decades. Okay, and it was invented by computer scientists Reves, Shamir, and Edelman in 1977. So you can see it's pretty old. And we'll get back to this. The security of the system. Okay, very interestingly, it relies on the computation. This computational problem. Okay, of factoring large prime numbers. What does that mean? Okay, we'll see that shortly. Okay, but yes, the security now, for now, just hold it at the back of your head that it relies on the difficulty, the a computation problem of factoring large numbers, large prime numbers, that is. So yes, how does RSA work? Now I talked about modular arithmetic and everything. Now we'll get into RSA. Okay, how it starts working and how we can probably encrypt data. Now, we start by generating two large primes, P and Q. Why primes? Okay, we'll get back again. Primes are very unique, as you would have learned in your school days. Okay, their factors are just 1 and they themselves. So if 7's factors are 1 and 7 itself. This is a very interesting property, okay, which we'll be using for security purposes. Now, we will be, okay, the second step of RSA involves computing a modulus n such that it is the product of P and Q, these primes we just selected. So n is nothing but P into Q, okay? And step 3, we calculate a very interesting value over here called phi of n. Phi you would have seen in physics mostly. We call it Euler's torsion function. So what is Euler's torsion function, you may ask? Okay, it is quite simply the count of all the numbers, okay, like before, for example, let's take 7, okay, the count of all the numbers before it, for example, from 1, 2, 3, 4, 5, 6, and all the numbers it is co-prime with. Co-prime means their GCD again should be 1, okay. If their GCD is 1, okay, and the count of such numbers before your prime or before your number itself is what you call Euler's torsion function. And for n, okay, logically, if you think about it, for a prime, okay, for 7, the count will be 6 because 7 is co-prime with every other number before it. Okay, and such is that for P, it will be P minus 1, and for Q, it will be Q minus 1. So you can extend this, and if, for example, n is P into Q into R into S, you can say P minus 1 into Q minus 1 into R minus 1 into S minus 1. So that's how you compute this very mystical Euler's torsion function. Then, step 4, we then set an integer e that is available to the public. Okay, this integer e, okay, we call it e right now, but it has a value, and this is public. And this is also what we call as the public key. Okay, RSA is an asymmetric crypto system. Note down if you want to. So this is where the public key comes from. So E is your public key, and it's available to every other person. Okay, whoever is intercepting communication, who wants to see what is happening. Okay, so it's that. So the final steps. Okay, step 5. Now this E, we choose a value, okay, that is lying between 1 to phi of n. And usually we take the value as 65537. You may think, why 65537? This is a very random value. I do not see any significance with this value. If you notice, okay, if you can tell, if you're a computer by any chance, this is a prime number, okay? And primes, okay, again, are very interesting. Okay, you can't just what to say, you don't have primes, like, you can't just factorize. The factors will be just one and what to say, the number itself. So there is a specific security, okay, with primes, which are a bit out of what to say. You can probably Google it up and research about it. You have Sophie German primes, etc. So yeah, so and when you are doing exponentiation, okay, modular exponentiation, this specific number, it gives you enough security and enough speed. It is observed that it gives you enough speed and enough security. So this arbitrary looking value is chosen. Okay. Then we determine D as E inverse mod phi of n. Finally, this phi value we computed has some value, I mean some importance, and you're seeing the modular inverse we just learned is not going to waste. It's used here. Okay, very interesting, right? This phi of n can be computed if you know the primes, right? P and Q. And E is a public value. So what is D? Yes, D is your private key. Okay, so E is your public key and D is your private key. So this is the relationship between D and E. So D is just the inverse of the public key under mod phi of n. And E would be the inverse of D, such that, okay, again, mod phi of n. So they are both inverses of each other. The public key and the private key are inverses under mod phi. You can say it as that. Okay, so we computed a lot of stuff. Now, encryption, our favorite part. This is the reason we are here for like, RSA. Encryption is done by raising your message to power E. Okay, this is not XOR. If you learned XOR is the symbol yesterday in Python, it's not. I mean, over here I'm using it as power. So it's M raised to E mod N. You might think M is your message. It's like, for example, if it's hello world, how can you convert that to numbers? Okay, that may kind of seems, oh, how? So you might remember ASCII values. Okay, but yes, I'll show you how to do that in Python in some time. But yes, M raised to E mod N is how you calculate this thing called ciphertext. Ciphertext is what you're going to be sending out in the channel, okay, between you and your recipient. For example, Alice and Bob exist, and Bob wants to communicate to Alice that, hello, my name is Alice. She is going to take her message, convert it into numbers, okay, raise it to the public exponent E, and then do mod N, the other modulus, which is P into Q, and then give out the ciphertext. And the public values are the E, the N, and the ciphertext in this. The message obviously is not public because you do not want someone else like intercepting your traffic and being like, oh, so your name is Alice. Okay. Imagine everybody can see your WhatsApp chats, like, with your grandma or something. That wouldn't be that nice. So this is where the security comes from. M raised to E mod N. So you're giving this number and you can't break this. Okay. And I will get to why it can't be broken. Now, decryption. Okay. So the curious and the more observant among us, all of you guys, would have observed that E and D are inverses. This is where the inverse part comes into play. So CT is just abbreviated like it's ciphertext. Okay. Now, if you take the ciphertext and raise it to D, and D is just the inverse of E, essentially you're doing what E into 1 by E, okay, in your integer terms, but not exactly in under mod phi, that is. Okay. So this E and D will cancel out each other, mod N, and hence you will be left with the M. You can see over here, M. So that's how you decrypt. Okay. So this person, the person who's decrypting, Bob in this case, needs to know the private key. Only then they can decrypt the message. Otherwise, nobody, okay, absolutely nobody can, okay, given E and N values, you just can't compute private key because you need to know the primes associated with the modulus. All right, let's move on. Yes, this is a small example. All right, you can have P is equal to 3, Q is equal to 11, blah, blah, blah. You can see all of the values over here. Okay, N is equal to 3 into 11, 33. Phi of N, again, You can calculate it as p minus 1 into q minus 1. P is 3 and 11. So you get 3 minus 1, 11 minus 1. 2 into 10 is 20. And you can see these values needs to hold up. The very important property, the public key and the whatever this you found, Euler's torsion function, needs to be 1. The GCD needs to be 1 for obvious reasons. We are going to compute a modular inverse. And think about it. You can't compute D without it being having the GCD equal to 1. We just saw that for inverse to exist, the GCD of the number A and B should be 1. So now in this case, we're just choosing 3 because 3 is the fastest number you can choose. Okay. Fast is like, it offers decent security and fast. So yeah, D such that D into E is equal to 1 mod 5 of n. In our case, D is equal to 7. 7 into 3 is equal to 1 mod 20. So key will be E of n and E and n 33, and private key will be D and n 33, and message is 7. You can decrypt using this. So it's simple. Now, you can see over here, 7 raised to 3 mod 33, it gives you 343 mod 33, and 343 mod 33 is 13. Okay. If you want to check it really fast, I can show it to you. So this is IPython. You can use your VS Code. So over here we have 343 and mod 33. Okay. I think everybody will be familiar with this operation, mod. So that is 13. Okay. And you can also do it as using the power thing for everybody to be on the same page. Well, this is what power does. So power 2 raised to 3 gives you 8. Okay, as you would have learned. Now we are trying to find 353, or let's take 7 raised to 3. Can we? Yes, 7 raised to 3. And the last argument, most of you guys wouldn't have studied this in school, is modulus. Okay, you can put a modulus 33. And you get 13 back. 13. So that's how you can calculate the ciphertext. Now, for decryption purposes, you can go 13 into 13 raised to 7 mod 33. You'll be getting this huge value. Obviously, 13 raised to 7 is a big value. Mod 33 again simplifies to 7. Okay, kind of like magic, but it's just math. Okay, if you know the math, it makes sense. Okay, you can probably revisit RSA at a later point, but yes, it's very cool. Let's move on. Yes, my favorite part about RSA, the security. I told you that RSA is secure, right? Due to you not being able to compute the prime factors. Think about this. No, so when you're trying to multiply two numbers, let's say 2 into 3, you can immediately do it as 6. 3 into 5, 15. You can easily do 5 into 3, 15 again. 5 into 10, 15. Easy. It's very fast. Computers do this very fast. It's so fast for the computers. The computers are basically programmed to be fast at this. But computers, again, suffer with square roots, taking square roots, doing division. Okay. And there is a particular problem, such as factoring. When you're trying to factor, like even in your pen and paper method, it takes you some time to factor out all the prime factors. Right. The same, funnily, applies to a computer. Computer takes a bit more time to factor, and this just grows exponentially as you reach huge numbers. And as I said, RSA lies on huge prime numbers and the inability of computers to factor them. Okay, you can see it relies on the difficulty of factoring large prime numbers, ensuring strong cryptographic security. So if they're hard to factor, okay, you saw that you need phi of n at the computing the private key stage. Okay, D is equal to E inverse mod phi. And phi, okay, phi of n needs to be computed using p minus 1 into q minus 1. We need p and q. How are you going to get p and q as an attacker? You can't. If you see n, okay, you'll be just lost. You can't factorize such a big number. I'll show you a big number after this. You'll be like, oh God, how would I factor this? Okay. And you just can't. Okay, even with the greatest supercomputer in this world, you can't factorize huge numbers. But okay, that's where RSA's huge security thing ends. RSA has this very, very interesting weakness. quantum computers can break RSA easily. Okay, you need a bunch of qubits. If you would have probably learned about Shor's algorithm, or not learned, you heard about Shor's algorithm somewhere. That like public cryptography is the quantum computers, and we should replace them with some other standards. Some, but yes, quantum computers that is a problem. Recent is now phased out or better what to say systems. Right now we use elliptic curves, okay, but again they also have the same weakness. It's faster, but there are more like an upcoming what to say crypto standards which will be used, and RSA will be scrapped. But RSA is the base for crypto system. It's relying on hard problem. And this hard problem can be extended to other crypto systems. There will be one hard problem. It's like a trap door. You can't go one way and you can't come back the other way. Just rely on RSA. You can multiply two numbers, but you can't factor them. I think we'll go. Yeah. So, um, so that is the issue. But again, RSA, even though I talked about quantum computers and quantum computers, it will take some time. IBM will take some time for quantum computers to be capable of breaking RSA. But RSA security can be compromised if weak keys are used or prime numbers are not chosen carefully. There are certain prime numbers for which you can break RSA. Okay, if the prime numbers are, for example, chosen together, like very what to say, very close by. Okay, if they are like very like if it's just the next prime, okay, you're gonna have issues. Okay, there's an attack for getting past that. And weak keys. Okay, even weak key like choosing E. Okay, for unpadded RSA. There's a variant of RSA called unpadded RSA or the textbook RSA, for which choosing E is extremely bad, and we will see a challenge. Okay, why it is bad. So the first one is not exactly an attack, but so there is this website called FactDB, which has some like the modulus you saw, and okay, it has some ends it is already calculated. For example, if you're multiplying two prime, huge primes, and you're getting an n, you can just post this result into FactDB. Okay, and now if someone else get that n, okay, it is astronomically low the chance, but if someone gets that prime factors now exist in FactDB. You might think, oh no, then you can just break RSA by just calculating all the primes. No, there's just too many primes, and you're just not going to do that. There's just too many permutations of all primes, and it'll take a long time. So yeah, and primes can be huge as well. So that's that. Then we have small e. That's the attack I was referring to. Choosing weak keys. Choosing a very small e is equal to 3, especially for padded RSA. So that's an attack. Fermat's factorization is the other one I talked about when the primes are chosen, what to say, together, like very close by. You have Fermat's factorization. Then you have stereotyped messages, which rely on some algorithm called Coppersmith. Okay. Then we have CRT on RSA, which is if you would have learned Chinese remainder theorem on RSA. We have common modulus. We have Wiener's attack. Then we have Bonnet-Durfee's attack. Then you will have a lot more. You just have the common Coppersmith and so much more. There are so much more attacks on RSA. RSA has existed from 1977, man. So you can expect a lot of attacks on it if it is not implemented properly. So yes, we will now see a very easy challenge. Okay. So I think challenge two. Okay. You can probably expect the challenge files to be on let's say the live stream. Okay. Now I'll try solving. Let's see. Let's go. Yeah. It's been So yeah, I was talking about factor DB, right? I won't be doing all the problems, okay? Just for you to understand what factor DB is. So we have the first prime. I mean, first the modulus. The small modulus. You will not expect. You might think this number is huge. It's not. Surprise, surprise. Okay. You can factorize. You can see that it is fully factored. FF stands for fully factored. And this number has two factors. There's a 10-digit 234765187, and there is 63642121501, two factors, okay, which already exists on FactorDB, okay. And so is that you will have this number, okay. You can also check. These are very small numbers. You can guarantee almost they exist. So there's two 10-digit factors. They are fully factored again. So that is kind of cool that they exist. Now, you can probably see for this number, okay, how this number also has a factor. It's fully factored. Believe it or not, it's 23 bits. Okay, I mean 20 digits. This is 23 digits. This is 45 digits number. I don't even know how to say that like in plain English. But yes, this is factored. So now you have P and Q. You can simply perform the declaration, and it will be done. You can try this number. Try this. Okay. So for your own reference. Now, like yeah, okay. Jump right into it. Yes. So now we'll be going through something called small e. Okay. Small e. Okay. In an attack case, when e is equal to 3, and you see some fancy notation, m very less than n. Okay. What does that mean? Okay. Let's say your e is equal to 3. Okay. It's a very small e, a small public exponent, a public key, and your message just so happens to be very tiny. Okay, happens to be very small. Let's say hello, and your n, your this particular n is huge. Okay, it's like a, let's say a 2048-bit number. Like even if it's a 45-digit number or 100-digit number, okay, you will have an attack where if you do m raised to 3, okay, this m raised to 3 will be smaller than n. So what does that mean? If m raised to 3 is smaller than n, you're basically not even doing mod n. It's like doing 1 raised to 3 mod 2. I mean, mod 3, let's take it. It will still be 1. Okay. It's not actually doing any mod. Okay. The number is too small. It's like, again, another example. Let's say 2 raised to 2 mod 5, which is just 4 mod 5. And 4 mod 5 is just 4. The modulus is not even working. For example, if it's 2 mod, like 2 raised to 3 mod 5, it will be 8 mod 5, okay, which is 3. That's when the modulus is actually working, that's when you're getting the remainder. So you're not wrapping around, like in simple terms, you're not wrapping around this clock of just, what do you say, n digits. So there's a very special attack where you can just simply take the cube root of the ciphertext or the number we give out to the public. We can simply take the cube root of this ciphertext and it will have your n. This is a very, very, what do you say, very stupid, attack. It happens when your message is too small. And yeah, there is a generalized case where if let's say m is possibly greater than n, like it's like on the same, what do you say, order of n, then you have this special formula that m is equal to cube root of ct ciphertext plus some k being an integer because integers are what is used under modulus and k into n. Okay, this works because the modular expansion. Okay, you can expand a modular equation, surprise, surprise, into an arithmetic equation. So you can represent n as so for greater, extremely bigger values like m raised to 3, extremely bigger than n. This k will be humongous, and you're not going to brute force, just try different values, exhaustive research, whatever you want to call it. You won't reach it. But yeah, for a generalized case, when m is like possibly greater than n, you can apply this. Or if it is not greater, beautiful, just cube root of n. So yeah, you have that. Now, again, a lot of values. Okay. Pause if you're watching it after the live stream. If you're not, you can just go ahead and the chat will have the pastebin message. So yeah, you can try decoding this. So yeah, let's get into the RSA part. This is probably the first time you'll be seeing RSA. Okay, so I selected the CT value. So CT is this number. So CT is this number, and we have N over here. Okay, and as our modulus, we'll be taking this. All right. So, and E is equal to 3. Now, we have CT, N, and E. We need to compute D. No, we don't have to compute. Okay, that's the entire point. Okay, you can see CT is extremely small. Like, it is laughably small. This number is laughably small compared to this. Okay, this is a humongous number. Now, even if you do raise to 3, it won't reach the size of M. Okay. Maybe if you want to see, yeah, it's not going to. So yeah, we can probably try this. You can simply take the cube root of this. Like ciphertext is ciphertext is what you're not trying to do, but CT is let's say go back. And yeah, ciphertext, this number is like small, extremely small. But yeah, maybe raising this to 3 is obviously you'll get to greater than n. But yes, now how do you go ahead and solve this? So you can do by importing something called integer nth root from SIMP. So it takes the nth root, whatever root you give it, like it takes the integer value of it. Okay. Now you can probably try doing that. Let's say we wanna, okay, this is a CT. CT is given here. We want to compute the integer nth root of the CT. This is what it will give you out. This is what it will give you out a number. This is what it gives you a number. True means it is an integer. Okay, that's what it says. So it's an integer. Now, this isn't a number. Okay, this isn't a tuple first of all. Okay, so we can simply do something like this, and we can just get the number. Okay, first in like 0th index, and we'll get the number. So how do we go about converting this into something meaningful, like a message? So we can import another module called crypto.util.number. From there, you will import, if you want long to bytes as L to B, okay, I'm going to go for long to bytes. So this is an integer. We are turning it into bytes. And I'm just calling as L to B over here for my own convenience. So yes, now I have this number, okay? Now, all I have to do is convert this into bytes. And you will see the encryption is broken. This is the message that was exchanged. And now we essentially cracked it. So this is again in bytes. If you want to make it look much more neat, you can obviously go in decode. And yeah, that's a string and flag you cracked small e. Very simple. You can even try out your own variation of this. You can implement RSA from scratch. Okay. Then you can try, breaking it using the small e attack. Okay. Try doing that. It's pretty fun. Okay. Really fun. It's a good exercise. So yes. So yes, that's all there is for today. Okay. We'll call today and thank you.